especially in these kind of sensitive settings where, sensors malfunction, sensors will send wrong signal. And if you have an automated system that's taking every one of those sensor readings as gospel and not cross-verifying it in any meaningful way, it can quickly get off on a tangent and lead itself down a very dangerous route. So right now, the fail-safe for that is human senses, intuition. They have the common sense that the AI models lack. So if it gets on a runaway because this one temperature sensor is, sending a bad signal and it's changing things in a way that's potentially going to be doing damage, the human will sense it vibrating, or they will see something else happen. They'll hear something, and they will go and they will shut that down. Hopefully, right? We can't always depend on that, and that's kind of what led us to our AI that cross-verifies the cyber-physical environment. The point of that is, look, these AI models are good, right? They can function even up to 90% accuracy. The problem is in production, 90% just isn't good enough, right? Being wrong 1 out of 10 times in these very sensitive settings is a disaster. And so what we were looking, oh boy, I'm getting ahead of myself here. What we were looking at is how do we layer up, kind of like what I'm showing here in this graph, different sensing inputs so that we can increase that accuracy from 90 to effectively 100%. And that's what we were seeing in the project. And so how did we end up encountering this? So we're doing a lot of combustion optimization, working with utilities and thermal plants. And like I'd mentioned, a lot of the data that we get is what we used to say in data science is dirty data, right? It's inaccurate. Certain parts of it need to be removed so that you can even do accurate modeling. Well, that's even more problematic when it comes to deploying, right? As annoying as it is to do training with dirty data, and then you have to actually explore the data and remove the bad parts. If you were running that in production and you had an inaccurate signal coming in, that would just be a disaster, right? That could honestly do severe damage, which is why more people are hesitant to actually deploy any fully automated systems, and they insist on keeping a human in the loop. But relying on humans is not particularly effective either. Often, especially with people retiring, the newer people coming in don't have as much expertise. They might not catch the nuance of these small little differences in operation that, the more senior people could. So this is what we saw as the need for this, right? So the setup that we did at EPRI'S lab was using, and you can see on the picture on the left, right? So that's a temperature vibration sensor that is attached to a pump. Next to that is just a decibel meter, so it's actually taking in. It's taking in just like the sound. We also did amps, but you can scale this up. This was just a small scale little project where we just did 3 different types of sensors. I mean, theoretically, you can scale this up quite a lot to like 30, 50 different sensors, depending on what the goal of what we're trying to monitor, what physical processes we're trying to monitor. And then what's so interesting, if you look at the right side, so this is just modeled in a 3D space, right? Because that's just more understandable. But as you look at this worked so well that you can visually identify the differences between the different operating conditions. And so distinctly that we were able to not only just tell that something bad was happening, we could actually understand and intuit what the bad thing was. Is this just, say, an operator error, or is this potentially an adversarial attack, somebody who has managed to hack into the system and is trying to do damage to the system? We could delineate between those within the data, which is very exciting. And then I think, what's harder to get your head around when I was talking about so many different types of sensors is this is a 3D model, but machine learning models can think in 30 dimension, not, 40 dimension, 100 dimensional. Now that's a hard thing for us to intuitively understand, but essentially looking at this and seeing these distinctions so clearly on a 3D model, if you can think of how much more distinct those classifications would be if this was done with 100x vectors moving in every possible direction, you can really start to understand why we were saying 100% accuracy on being able to detect potentially damaging events within the physical systems. Jeremy, I feel like you sing this song better than I do. Is there anything else you want to add about the work we were doing in the lab there?
Oh, hey, Hayden, this is great. Yeah, maybe if you could you talk a little bit about the overall setup that we had in the lab and what that looked like?
Yeah, great point. So the main things that we were trying to monitor were the main areas where we would be worried about damage, right? So we were monitoring the valves, we were monitoring the pumps. This was a throughput system, so this was just water running through. And then there were collection tanks. And interesting, actually, while we were doing this study, at one point, there's a sensor on the collection tank that's monitoring the level of the tank. And that sensor malfunctioned while we were performing this experiment. And we actually got that. And it was like, oh my God, I mean, this is exactly the problem, right? It's like when one of these things fail, if we don't have built-in redundancy, if that was being done with none of us in the room to be able to see that the tank was about to overflow, it could have overflowed and caused damage. And it's like that's what we're really trying to get in front of is like how can we add these kind of like relatively cheap external sensors to be able to create a system watching the system, to be able to increase the redundancy and be able to really understand anything, be it a mistake or an attack that could often, hurt operational resiliency. So I mean, yeah, I think what else am I missing? Is there anything else about the project? I mean, I guess one thing that I would love to articulate on this too, which I think is so exciting about it. We did this for the pumps because that was, the setup that was available. But this could be used for any physical operation, right? Anything that you are doing that you need to monitor the operational integrity that makes a sound, that vibrates, that does anything. This could be an applicable technology. And that's probably a good segue into uh, what we've been up to since working with EPRI. We actually did a project with Air Force Research Labs, and we're currently doing that, which is monitoring a chiller, which actually keeps the integrity for their quantum labs. And same thing, if this, has any slight deviations, this could damage the quantum computer, which is, a big deal to them. And then interestingly, for the thing that they're very worried about, which is also applicable for utilities, is, adversarial attacks. So how do you catch those, right? It's like, we have systems in place to try to catch that within code, within packaging, but it's like if something gets through, how do you detect if somebody has been able to take over and is actually manipulating your controls? You can think like Stuxnet and certain other viruses like that. Prevention is good, detection is a must, and that's also what we're getting at, and that's something that the Air Force is very worried about, and that we're making the project about. Jeremy, I think I saw your hand go up. Please feel free to jump in anytime. By the way, it's always good when you and I have a conversation back and forth. It's more interesting for everyone.
Yeah, yeah, thanks, Hayden. So if you don't mind going back to the other slide, just a couple of things to elaborate on. So really to provide a little bit of context and the testing that we got to work together on. So this leveraged the instrumentation and control flow loop that we have in Charlotte. So if you think about it from an overall process perspective, it's we've got two pumps that have two big loops of water with a surge tank. Pumps water in a big circle and a big loop, and there's a few different configurations that we can put that in, whether the loops are in series or parallel, and as well as some different control strategies as well that we can deploy. So we really use this as an opportunity to provide physical data that we could use to provide indication of, in this case, a cyber instance or cyber attack. And what we did is we stepped through a couple different mechanisms or causalities of how we introduce those cyber attacks into the control system. And what we did is you'll see here over to the right in this graph, it says pump fighting the valve. And essentially what that means there is that the normal mode of operation for this flow loop system was using variable frequency drives to vary the pump speed. So that's kind of the normal mode of operation for that, to maintain water level as well as maintain normal system operation. But we also have a discharge valve that we can throttle as well. And so what we did is we introduced a simulated cyber event where set points and control strategies were modified. And really the goal there is we wanted to be able to not just identify anomalies, because that's pretty typical in monitoring and diagnostic space, but we also wanted to get into the classification. So we wanted to be able to distinguish potential causality. And so when we look at these you'll see here the dots that are in red, that they're labeled the pump fighting the valve, as well as the valve open at 50% and valve open at 75%. Those were the examples where there was a kind of quote unquote simulated cyber event. The cavitation event was one that we introduced by lowering the tank level. So this one was a little bit easier to detect because, of course, when a pump's cavitating, you can hear it across the room. But really what we were trying to do there is distinguish a normal, and I say that with maybe air quotes, but some kind of operational failure, or where there was a valve misposition, still something that would be beneficial to facility operators to identify, but something that maybe wouldn't be caused by a cyber event. So just to provide a little bit of context to the testing setup.
Perfect. Like I said, you always explain it better, so it's great to have your input on this. And I think, to piggyback on what Jeremy was just saying, and what's another interesting aspect of this is, even sometimes when there are kind of some types of alerts or alarms for things, it goes back to if there's just a problem with one of the sensors or some kind of like ghost in the machine, so to speak, it can end up sending too many alarms. They end up like a car alarm back in the 90s, right? It's constantly going off. Nobody assumes it's actually a disaster anymore. Well, that's, problematic if you end up training the people that the alarms are, to be ignored. So this is a way of reducing the false alarm so that when you actually get an alarm, and then kind of like we were saying, if we can delineate between just like a small operational hiccup to like this is actually somebody who's trying to do damage to this system, you can send different types of alarms at different, urgencies. And I think that's the other very interesting thing is like being able to build a trust in these systems, but also making them useful and deployable. Because if somebody just shuts off the alarms because they get one every day and they're always wrong, well, that's not, I mean, that's no better than having no system at all, kind of thing, right? Uh, so then, yeah, I mean,
And there's,
yeah, go ahead.
I'll just mention there's one question in chat from Sunny. And the question is this audio data?
This was actually from the triaxial accelerometer. So the way that you measure vibrations with the Advantech is it does just the different access planes. And so this was just measuring the position of the X, Y, and Z on the vibration sensor alone. So yeah, like I said, it's hard to graphically represent layering up all those different data and fusing those data sources together. But what I find so exciting about this project is the fact that you can look at just one of the sensor things and you can visually see the difference. That just shows that it is a great use case for machine learning models. Are there any other questions in the chat? I don't know that I'm seeing those. Is this the ThermoAI meeting? Oh, yeah, this is. You're in the right place. Okay, so I think that's it for the questions that I'm seeing so far. So then moving along, the thing that we are doing with the Air Force, yeah, like I said, once again, is they obviously are very worried about operational, especially spoofing, which is another thing that I think not a lot of people are thinking about. So if you have an automated system and you are relying on all of your sensors being accurate, that actually makes you even more vulnerable in some ways because all you need to do is you don't need to change the whole system. You just need to spoof one of those inputs. And then that can potentially, if there's no redundancy built into that system, throw you down a whole rabbit hole and do a lot of damage. So an interesting example of this, and you guys can look it up, there was a performance artist did this video in Berlin where he filled a Radio Flyer red wagon with 99 cell phones that were all in Google Maps and just walked it down the street and was able to create a traffic jam in Google Maps. And ultimately, Google is some of the most sophisticated AI in the world. But even that, it's assuming every one of those inputs from a cell phone logged in is an actual car. Now, human common sense is you could look out your window and see that it's not a traffic jam because that would sound different, that the street would vibrate differently. There would be other signals than just taking that one input. But I think that is an interesting example that they were able to spoof Google, which is one of the top in AI in the world, with what, $500 in a wagon kind of thing, right? And it's like they were able to make Google's own systems think that there was a traffic jam outside of their office so simply. And you compare that to nation state actors or any other thing that are far more sophisticated and have a lot more funds, and you really get the weight and magnitude of this problem, right? That trying to stop all of those piecemeal is a pretty daunting task. So you're really going to need something monitoring the physical environment that can catch everything, right? Just relying on humans to be around. I mean, another one of the things that came up recently was the one down in Florida, Oldmar, Florida. Somebody was able to log in through a remote access and was able to change settings and was dumping all the lye into the water supply for an area just north of Tampa. And it just so happened that a human operator was walking that section of the operation and saw it themselves. But if they hadn't been there at that exact time, disaster could have happened. And I think we're seeing more and more of those as we're getting more and more things online and more things are moving towards automation. We need to build in more sophisticated fail safes so that we can actually be implementing those things and trusting them versus implementing them and then everybody ignoring them. And I think that's the kind of real thing on this. So before we kind of open it up with questions, I think that's the main benefits that we are seeing for this is a cheap, easy way to add redundancy to any system. This is modular. This sits outside of the current system, so it doesn't increase this attack surface. It's totally separate so that even if a system is hacked, this one would not be hacked. Other than just cyber events or adversarial, this can just catch potentially damaging events such as, a new operator who makes a mistake, leaves a valve in the wrong position, and can still be doing a lot of damage. This can also catch that. No matter what the physically damaging event is, no matter what the cause is, it can catch it. And then, like we were saying earlier, what's also very exciting about this is it could start delineating and giving a different understanding on, is this a run of the mill or is this something that's really disastrous, and then actually prompt in, uh, you know, better response times on these things. And then finally, I think the main thing that we're seeing is there is certainly a mistrust, and like everything I'm saying here, it's a somewhat warranted mistrust of AI systems and AI recommendations. And I think solutions like these are going to be very important for enabling a lot of the digital transformation goals, right? How do we show people enough of the benefit and that they feel like, hey, this is not a car alarm that it's like, oh, it's always wrong. It's like, no, if this is our fire alarm in your apartment kind of thing, right? It's like, if I'm getting this alarm, I don't have to spend the first 30, 40 minutes understanding if it's real or fake, right? If we can get that accuracy up to 100%, that is going to be fundamental on every company achieving their AI and digital transformation goals. And I think this is a very uh, cheap, easy way to accomplish that. So those are the main things. I would love to open it up to questions and hear what everybody has to think about it.
So Aiden, I'll start it out. This is Jeremy. So a couple questions on the Air Force project. Could you talk a little bit about some of the specific use cases that they were interested in implementing this type of approach, and were there any maybe gaps that they were trying to fill?
Yeah, absolutely. So I mean, for them, one of the main concerns, obviously, is maintaining mission readiness is a huge issue for them. So like operational resiliency is a major goal. But them, more so than most, they are very aware that they got a target on their back, right? So critical infrastructure, in any type of, war scenario would be a very real first concern. And currently, it's like this is kind of what I'm saying is like it wouldn't be obvious for the operators if somebody is in your SCADA system and changing the values, it wouldn't be obvious that that wasn't the system operating normal, right? You can do what's called like a replay attack where you show old sensor signal and you replay that while you make changes to the PLC controllers. And any of the systems that are currently connected to online systems are vulnerable for this. Or worse yet, I mean, there's a great book on this, Sandworm, which I recommend if you want to have more trouble sleeping at night. They talk about the innocuous ways that they're able to infiltrate a lot of these industrial control systems. And often these are vulnerabilities that are embedded into just like a PowerPoint or a PDF that the moment it comes in touch with a Rockwell, so if it's any contractor or anybody plugging in, that thing can stay there, even in an air gap system. Trying to catch 100% of these just seems impossible. But being able to understand when it happens and being able to warn people and then understand that when these things need to be taken offline, kind of rewritten because they have been affected, I think that is the main thing that the Air Force is very worried about. And then I would say one other one on top of that, just in general, the thing that they are mindful of, probably more mindful than most groups. So we were working with the Air Force Research Lab that's responsible for AI. And the thing that happens often in most industries, but especially with the military, because things being classified, it tends to be that every sensor has its own group who's responsible for it. And so instead of fusing that data, because it ends up all getting siloed, it ends up that each information has its own group, and then those groups all get together and talk. But if you think about it, that's actually pretty disjointed, right? That would be like your eyes, your ears, your sense of smell, all having their own representative, and then they have to come together and have a consortium on what you're seeing in front of you. Right? To try to detect what a horse is by all of those things describing it. What humans normally do is we naturally fuse all that data together to have more accurate understandings. And that's kind of what we're trying to do here is how do we take all those physical sensing and then fuse them together so common sensing to increase common sense of these AI devices.
Yeah, great. Thank you.
Anything else, anybody? Don't be bashful. All right, Jeremy, you got any more stock ones or?
Yeah, no, this is a really good conversation. I think to me the interesting part is trying to bring all of these dispersed data sets together to provide better modeling as well as better modeling accuracy and precision as well for these different use cases. So yeah, I guess one question I'd throw out to the group. I mean, has anybody else on the call started to look into these different use cases, maybe for different applications, or maybe look at taking a similar approach? Give folks a couple of minutes to type things into chat, or feel free to take yourselves off mute as well. Yeah, I'll mention that this is an area that we've done a lot of work in as well, with an EPRI, also working with different stakeholders. So tying some of the in generation space monitoring and diagnostics data together, getting that physical information, those physical data sets out from, say, a historian or some of these bolt-on third-party sensors as well. But bringing that together with the security data as well. So looking at it from the perspective of what's the network traffic coming across the network doing, and also looking at different security alerts and alarms and things like that. So similar to some of the things that Aidan has talked about, we see a similar challenge in security space where at some point, if you have so many alerts, they're not actionable. So really part of the goal here is to bring this together to make the information more actionable for either security operations staff or plant operations staff as well. So I guess one other question. So Aidan, could you talk a little bit about what some of the next steps are?
Yeah, absolutely. So we are doing the project with Air Force Research Lab right now, and the goal will be after that, really understanding where else and what other types of sensors we can be kind of adding to other critical infrastructure to really shore it up, kind of thing, right? So I think that's we did 3 sensors in the project that we did with EPRI. What's going to get very interesting and exciting is like what happens when we get up to like 30, what happens when we're monitoring. And actually, I mean, that's another interesting point. So the project that we did with EPRI was actually only over 3 days, which normally from, a data science perspective, that's, murder to have such a small data set. And we still got great results. So I think this is the very exciting thing is like as we're building this out and as we're kind of further training these things, like what further insights and understandings are we going to gain from running these things for months or years in various different scenarios and understandings? And then what other nuance will we be able to intuit kind of thing? So that's the main thing now is like rolling it out with Air Force, and we're still looking for other utility customers who would be interested in being involved early on and helping us shape and form this new project. So if anybody on the call, if this sounds interesting to you, you take my email and please feel free to reach out.
Yeah, thanks, Aidan. Any other questions for Aidan?
Aiden, this is Greg Adams. Earlier in the presentation, and maybe I missed this because I was distracted, but you talked about some of the dirty data that you were getting in. And I thought maybe one of the things that you were going to do is talk about how you would use artificial intelligence in order to actually automatically clean data. Is that an area or a space that you guys are looking at that, that I can see a lot of applications for that. So that's why I was asking.
That is a very good point. Yes, so it's funny. I always wonder sometimes how much you want to get into the weeds on these things, but that's exactly a lot of what we're looking at, right? One, this helps with deployment, but then it's exactly that as well, right? That it's like, if we can be kind of understanding what is normal, and then if one level spikes, and then that we don't see a concurrence through other physical signatures, you're right, we can immediately say, oh, well, that's just bad, so let's just drop that out immediately. Whereas right now, that is a very manually intensive, like it takes a high cost data scientist to look through, explore the data and look at it and be like, oh, well, that can't be right. So let's just clean out that section. But you're right, that could definitely be an automated data cleaning pipeline. So yeah, good for you for picking that up. That is definitely something that we have in our purview.
Okay, great, thanks. And I really love the 100-dimensional idea. I think that's pretty fascinating. So great presentation, thanks.
Thank you, Greg.
All right, great. Any other questions for Aiden?
Doesn't look like there's anybody else, so we want to thank you, Aiden and Jeremy, and all of our attendees for taking the time to do this. We appreciate that. We absolutely wish the best for ThermoAI going forward. And again, we appreciate your attendance. If you are interested, this recording will be posted on our Incubatenergy Labs site under ThermoAI's project for 2021. So if you wish to review it, you can do so at any time. It will have the recording and the slides. So if you have trouble finding it, please let me know and I will be glad to send it to you. It will take about 3 to 5 days for that to get posted. So again, thank you for everyone and have a great rest of your day.